Hello, everyone. I'm Norman Wahlberger. Thanks for joining me on this adventure. We are giving you some advice, and I want to make contact with important ideas from calculus today and shift your understanding of functions towards formal power series, which are sort of combinatorial versions of power series. This is a very important shift because from a logical point of view, I'm going to argue the current understanding of functions as things that input real numbers and output real numbers really doesn't work computationally, okay? But there is an alternative that the combinatorialists have been building up for, actually quite some time. And this is really the stronger and more solid foundation for a lot of analysis. And we're going to look very explicitly at two of the most important and central power series, the exponential and the logarithm Pauli series. But I'm going to give them to you in terms of two variants called E and L, which are going to fit more naturally with our understanding of the composition operation on Pauli series. Okay, so let's start with formal power series. Okay, this is a concept which probably was officially introduced first by Ernst Schroeder in a paper Über iterierte Funktionen in Math Annals, or Annalen perhaps, in 1871. And then considerably later, Ivan Niven wrote a paper called Formal Power Series in the American Math Monthly in 1969, which was quite a celebrated paper and really, I think, brought this to the wide attention of the mathematical community. Steven Scheinberg also wrote a paper, Power Series in One Variable, the following year, which also sort of gave an overview of things. And in terms of sort of a comprehensive treatment, you can't really go past Richard Stanley's monumental work, Enumerative Combinatorics, in 2 volumes, which was published in 1997 and 1999. And there's quite a lot of information about formal power series there. So the basic idea is to look at power series not as functions, but as sort of formal polynomials that just keep on going, or we call them Pauli series. And in fact, this point of view is really historically going back to Euler, at least, who definitely thought in this direction, and no doubt almost really to Newton, who appreciated that power series could be thought of as sort of algebraic equivalents of infinite decimals. So I want to reorient you, since I'm trying to give you advice. So I think it's really important that you let go of some of the programming that you will have been subjected to. Okay, as modern students of mathematics, you've been oriented to think about the function concept as sort of all-pervasive. In any situation, we look around to define a function. We think of a function as something that inputs one thing and outputs something else. It's a dynamical thing. Okay. And of course, the standard repertoire of analysis is full of functions, elementary ones, like f of x equals x squared. Not so elementary ones like sine of x, log of x, tan of x, arc sine of x, the zeta function, the gamma function, etc., etc. But if we look carefully at these things, okay, we see that there's actually a serious problem. The serious problem is that we're not actually able to evaluate these things, with the exception of f of x equals x squared. That one we can actually evaluate. If I ask what's f of 7, it's 7 squared, I can calculate that as 49. If I ask you what is sine of 7, or tan of 7, or gamma of 7, well, gamma of 7 we can do, a gamma of, say, 7 over 3, or zeta of 7, or most of the functions in modern analysis cannot actually be calculated exactly. Approximately, yes, but not exactly. And really, from a logical point of view, that really excludes them from being properly defined mathematical objects. They're really not. They are objects from applied mathematics that we import into pure mathematics and sort of pretend that they are now correct, precise, pure mathematical objects when they are not. Okay? So I want to suggest to you politely that it's not a question of opinion here. It's not that, oh, well, we could take this point of view and we could take this point of view. We could either think about these things as functions or as power series, formal power series. No, okay. The functional approach is logically weak. It's logically compromised. The formal power series approach of the combinatorialists gives us an alternative, more solid foundation. Okay, so having said that, and this is something that I'm going to have to repeat over and over again because our programming is just so all-pervasive. But anyway, let's look at two of the central examples. Okay, the exponential and the logarithm Pauli series. And I'm going to introduce some variants called capital E and capital L, and you'll see why. This fits very nicely into this framework of composition of Pauli series. So let me remind you that if we have two Pauli numbers, P and Q, so these are like finite polynomials, the composition of P and Q is sometimes denoted P circle Q, okay, which is another way of saying P of Q. And that this kind of composition extends to Pauli series, where the terms are ongoing, provided that the Q inside here is grounded. In other words, that it can be written as a power series or Pauli series in alpha with no constant term. Okay, that's the crucial property that allows such a composition to be in general defined. And then once we have this notion, we can say that a Pauli series P has a compositional inverse Q, precisely when P circle Q equals Q circle P equals the compositional identity, which is just the Pauli series alpha. And then I mentioned a theorem like this last time, that Pauli series P, C0 plus C1 alpha plus C2 alpha squared, etc., has a compositional inverse precisely when there's no constant term, when C0 equals 0, and when this C1 term, the coefficient of alpha, is non-zero. And in this case, the inverse Q is unique and can be computed sort of term by term. So in particular, a Pauli series must be grounded in order for it to have a compositional inverse. Right? The grounded condition is that C0 equals 0. But a little more is actually required. We also need that this C1 is not 0. Okay, so now a central object, the exponential Pauli series, exp. Okay, here it is. It's a Pauli series that's written in summation notation like this. Summation k equals 0 and then onwards, going through natural numbers, proceeding further and further. 1 over k factorial times alpha to the k. And then explicitly the first few terms, 1 plus alpha plus 1/2 alpha squared plus 1/6 alpha cubed, etc. We have the various factorials appearing here. Now this is not grounded, right? It's not grounded because there's a constant term, which is 1. So if we want to move into a domain where we can talk about compositional inverses, we're going to have to modify this by stripping away the constant term. So we're going to do that, and we're going to give that new thing, this sort of grounded version of the exponential Pauli series, a new name, call it capital E. So here's capital E, which is exp minus 1. We'll call that the grounded exponential Pauli series. Here it is right here. Okay, it looks just like the exponential, except that it starts with alpha. Alpha plus 1/2 alpha squared, and so on. This is further unital. Maybe I should put that in bold. So unital is referring to the fact that this term alpha actually has a coefficient of 1. It's not just non-zero, it actually is equal to 1. That's particularly pleasant. Okay, and so now we come to one of the great miracles of calculus. Just a beautiful fact that has manifestations throughout the subject. And I want to emphasize that this is in the context now of this framework of power series or Pauli series, okay? The compositional inverse of E, okay, this is now a Pauli series which satisfies our conditions, so we know that it has a compositional inverse. And now we're going to say what that compositional inverse is. The compositional inverse of E is what we're going to call the grounded logarithm Pauli series. And we're going to call it capital L. And here's what it is. it's this series here. Alpha minus 1/2 alpha squared plus 1/3 alpha cubed minus 1/4 alpha to the 4th plus etc. Alternating in sign. The denominators here are growing much slower than over here. Here they were factorials. Here they're just natural numbers by themselves. Okay. So in summation notation, summation k equals 1 onwards, minus 1 to the k plus 1 over k, alpha to the k. So when k is 1, we get alpha, we get a 1 in the denominator, and we get minus 1 squared. So we get a positive term there. Okay, so in calculus courses, you usually don't see this thing defined. Usually there's another so-called function called the log function, written either with the symbol log or sometimes ln with an ln. And what we're expressing as L would be in a traditional calculus course expressed as log of 1 plus x or ln of 1 plus x. The actual ln or log function in quotes in calculus is not typically defined in terms of a power series. Because that's actually problematic. But it's defined in some other fashion, often as an integral or sometimes as the inverse of exp. Okay, but what we want to do is we want to separate ourselves from any understanding of these things as functions. Okay, so we're going to stick with a purely algebraic approach here. Functions are not required, and so the definition of L, or the way this L comes about, is we're looking for the compositional inverse of this exponential e. Okay, so let's look at some properties of E and L. Okay, so these two power series have lots of remarkable and important properties. And when we want to express some of them, it's convenient to move to bipoly numbers or bipoly series, where we think not just in terms of alpha, but also beta. So you may recall that the alpha poly number is the vertical list 0, 1. Well, there's also a horizontal list 0, 1, and we call that beta. And that way we can think about sort of bipoly numbers, polynomials in two variables, alpha and beta, if you like, in terms of arrays, two-dimensional arrays of coefficients instead of just one-dimensional lists. Okay, so in this context of sort of expanding our arithmetic to include both alpha and beta, then we can express this very important property of the grounded exponential polyseries E this way: that E of alpha plus beta equals E of alpha plus E of beta plus E of alpha times E of beta. And so before I go on to the grounded logarithm, I think it's good for me to try to justify this. So let's see if we can sort of convince ourselves of this. All right. So let's define first of all E, say, of alpha, and I'll just grab the first few terms of this, maybe up to degree 6, let's say. All right, up to there, and we'll make that definition. And now let's look at E of alpha plus beta. Okay, what is that? So there it is there. Let's expand this out. And let's now sort of cut this down so that we're only going, well, I guess we're only going up to degree 6, aren't we? Going up to degree 6. Okay, fine. And that was the left-hand side. And now let's look at the right-hand side. E alpha plus E beta plus E alpha E beta. Let's see what that looks like. There's alpha, there's beta, and there's the product. Let's expand that. So we've expanded it up to here. And okay, how does this compare with this? Well, if we sort of cut down things in the first expression, I only went up to a total degree of 6. Okay, so if I only go up to total degree of 6, I am going to kill these guys. These are all of degree more than 6. Any other ones? Yes, this one here is more. Going to just go up to degree 6 and no further. Any more? Oh, this is bigger. These terms are also bigger. That one's bigger. How does that look? Do I have just terms up to total degree 6? Okay, so let me just expand that out. So that's what it is. And up here, what I had originally, let me just look at that. Okay, so I'm comparing this with this. Are these all the same? Oh, I still have to remove some further ones. I forgot. These are all bigger degrees. Get rid of them. Okay, I think I've done that now. So now if you compare this thing here, I've gone to up to degree 6, total degree 6, and this expression here, total degree 6, and it looks like these things are the same, right? This thing here is the same as this. So we'll say these two expressions agree up to total degree 6 in alpha and beta. Okay, so that convinces us at least that this is very likely a true expression. It's not a proof, of course, but it's on the way of a verification. So that was for this grounded exponential Pauli series. Now what about the grounded logarithm Pauli series? Well, here is the crucial relation for it, which is very analogous to the one for the grounded exponential. It's that L of alpha plus beta equals L alpha plus L beta. In fact, I might just juxtapose these two things. So I might just put that there to remind us. So that's the relation for the grounded exponential. Here's the relation for the grounded logarithm. L of alpha plus alpha beta equals L alpha plus L beta. And these two relations are, of course, intimately connected with each other because these two Pauli series are compositional inverses. And I remind you what that means is that if we take E of L, we get alpha. And if we take L of E, we get alpha. So how do we prove relations like this? Well, it turns out that there's a highly non-obvious tool here that people have realized that one can use to establish all kinds of interesting relations here. It's a very general kind of tool. It's the Faulhaber derivative, D. Actually, I might call it Faulhaber capital D derivative. That's what I typically do in the algebraic calculus course. So this, of course, plays a major role in the algebraic calculus, and we are emphasizing that this is a formal operation on polynomials or polynumbers or Pauli series. It's defined just in the simple way that d of a pure power alpha to the n is n times alpha to the n minus 1 for any natural number n equals 0, 1, 2, 3, etc. With the understanding that when n is 0, in other words, d of a constant or d of 1, we get 0. And then this is extended linearly. So if we want to take d of this Pauli number, 2 plus alpha minus 7 alpha cubed plus alpha to the 5, well, and it's d of 2, which is 0, d of alpha, which is 1, d of minus 7 alpha cubed, which is 21 alpha squared, and d of alpha to the 5th, which is 5 alpha to the 4th. And then it's elementary to extend this to Pauli series. You just apply the d to each of the individual powers in a Pauli series. So then there are two important rules that this formal Faulhaber derivative satisfies, and I really want to emphasize that this is quite logically independent from the usual understanding of a derivative as a slope of a tangent, to a function. We don't have functions here; we just have these Pauli series, and it's also independent of any kind of limit of ratios, like f of x plus h minus f of x over h, some limit of slopes of secants or some such thing. Okay, this is a purely algebraic thing, does not require any infinite processes, and it also has actually not really require a prior understanding of so-called functions. We're just operating in this purely algebraic world. Okay, so here are the two crucial sort of rules. The product rule for the derivative d of p times q is p times d of q plus q times d of p. And the derivative of a composition, so-called chain rule, d of p circle q equals d of p circle q, that's one Pauli number, times d of q. And these formulas also extend to Pauli series when they are defined. In other words, when these compositions, for example, are working, okay, which would require Q to be a grounded Pauli series. Okay, so now we can go up to the L and the E Pauli series, and we can calculate their formal derivatives. So d of L, what is that? Well, let's just go and pull these things again for us so that we can remind ourselves. So let's grab this E and that L. Come down here. Okay, so I'll just stick that over here. So there's that one there, and then there's that one. So here's the definition of E, and here's the definition of L. So if we take the derivative of L, it means we're just taking the derivative of each individual term. The derivative of alpha is 1. The derivative of minus 1/2 alpha squared. Well, the 2 comes to the front, cancels with the 2 that's there, and we just get alpha. And then the next term, the derivative of 1/3 alpha cubed is plus alpha squared. The derivative of minus 1/4 alpha to the 4th is plus 1/4, etc. So we get a series which has a natural interpretation as 1 over 1 plus alpha. That's a rational function. Okay, that's like a geometric series that algebraically is equivalent to 1 over 1 plus alpha. So the derivative of L is a very pleasant thing. Okay, and this is a very important relation. What about the derivative of E? Well, you'll probably all know that the derivative of E is more or less itself. But remember, this is not quite the exponential because we've stripped away the 1. So if we take the derivative of this thing, we're going to get 1. Plus the derivative of this thing is alpha. The derivative of this thing is alpha squared, but there's a 2 on the bottom. Okay, the derivative of this one, the 4 comes out, cancels with the 4 and the 4 factorial here, and we just get a 1 over 3 factorial. So what we end up getting is the usual exponential Pauli series, or in terms of capital E, it's 1 plus capital E. All right, so now let's put these things together to try to understand what happens when we compose L and E. So let's do it in this order. So let's apply D to this composition L of E. In other words, L circle E. So D of L circle E. According to this chain rule, that's going to be D of L circle E times D of E. Well, D of L, we've calculated, that's 1 over 1 plus alpha. So we can put 1 over 1 plus alpha there. And we are taking the circle of that, we're composing that with E. What does that mean? Well, it just means that we're replacing the alpha with an E. And what is D of E? Well, D of E is 1 plus E. So we're getting 1 plus E times this thing evaluated at E is 1 over 1 plus E. So we get 1 plus E over 1 plus E, which is 1. So the derivative of this Pauli series, L circle E, whatever it is just the constant 1. Well, that means, that's a very strong condition, that means that this L circle E has to only consist of constant and linear terms. In fact, the linear term has to be alpha because the derivative is going to be 1. However, we don't know what the constant term is because when we take the derivative, that's killed, that's sent to 0 no matter what it is. So to evaluate what this C0 is, we can plug in a simple value. We can plug in what happens if we replace alpha with 0. We can evaluate left and right hand sides at 0. So L of E of 0, well, E of 0, here's E. If you plug in 0, you're going to get 0. And so you're going to get L of 0. And when you plug in 0 for L, you're going to get 0. So you're going to get 0 on the left-hand side. The alpha is 0, and that proves that C0 equals 0. And so that there's no constant term, and so L circle E is actually alpha. So we've proven this strong compositional connection between E and L in this sort of magical way by utilizing this formal derivative. It's a very powerful technique. So now we have two central objects of calculus, and now the kinds of considerations that we've been investigating now expand much further.